Okay, so you know how you were asking about Ku-band pyramidal horn antennas?
Yeah.
Well, someone sent us this master's thesis
Oh, wow.
by Arvind Roy,
Okay.
guided by Mrs. Isha Puri from lovely Professional University.
Uh-huh.
And it's a serious deep dive into these antennas.
Nice.
They even used HFSS software for it.
Really?
Submitted in May 2015, so it's a little older.
Mm.
But, you were especially interested in how these antennas are used for satellite beaconing
Right.
and television broadcasting within that Ku-band range.
Yeah, the 12 to 18 gigahertz range.
Yeah.
And this thesis seemed like the perfect place to really unpack that for you.
So maybe we should start by getting a clear picture in our minds.
Okay.
What exactly is a horn antenna?
Well, you can kind of picture it in the name, right? It's shaped like a horn.
It flares out.
Yeah, it flares out, and that shape helps to send and receive those electromagnetic signals more effectively.
Okay, so why is the pyramidal horn antenna so interesting?
Well, pyramidal horns, they have some real advantages. Well, first, they can have a really high gain,
Meaning?
meaning they can really focus the signal in a specific direction.
Okay, that makes sense.
Then there's the VSWR.
Voltage standing wave ratio.
Right. The VSWR and pyramidal horns tend to have a low VSWR.
And that's a good thing.
Oh, yeah. A low VSWR means that the antenna is really well matched to the equipment it's hooked up to.
Less power wasted.
Exactly. Less
Yeah.
power is reflected back, so you get more efficient transmission.
Nice.
And the other great thing is they can work over a pretty wide range of frequencies.
So they're versatile.
Very versatile.
Yeah.
You see them used in so many places, from aircraft to spacecraft.
I remember reading that they use some pretty high-tech tools to design and test this antenna.
Oh, yeah. They went all out. They used Ansoft HFSS V12.1 for designing the antenna and then simulating its electromagnetic behavior.
So they could test it out virtually.
Yeah, they could basically see how the antenna would perform without actually building it.
That's so cool.
And for all the heavy number crunching, like the calculations they needed to do to fine-tune the design,
Uh-huh.
they used MATLAB 2010B,
Makes sense.
and then to visualize some of the design parameters, Digigraph V.2, to create graphs.
So they really had a whole toolbox of software to tackle this.
Absolutely. A really powerful set of tools.
Okay, so our mission here is to really understand these Ku-band pyramidal horn antennas.
Right.
But where do we even begin with something like this?
I think a little bit of historical context might be helpful.
Okay.
So, antenna engineering has a rich history, and the thesis touches on some of the key figures.
Yeah, who?
Well, there's James Clerk Maxwell.
The guy with the equations.
Yeah. His work in the 19th century laid the foundation for our understanding of electromagnetic fields.
Pretty important.
Absolutely. And then you have Guglielmo Marconi.
The wireless transmission guy.
Exactly. His experiments really sparked the whole field of wireless communication.
So those are like the grandfathers of the field.
Yeah, you could say that, but if we focus specifically on horn antennas, the thesis credits Sir Oliver Lodge.
I don't know that
He
one.
did a lot of work on microwave waveguides back in 1894,
Okay.
which, as we'll see, are really important for horn antennas.
Okay.
But then there's Sir Jagadish Chandra Bose.
What did he do?
He designed what's considered the first horn antenna around 1897.
Wow, so early.
I know, right? And what's really fascinating is that his design used a circular waveguide and a circular opening,
Interesting.
and it operated at really high frequencies around 60 gigahertz.
That's amazing for the 1890s.
It is, right? And all this was happening in Calcutta, now Kolkata.
So he was way ahead of his time.
Absolutely a true pioneer.
Okay, so then World War II happened.
Right, and that's when rectangular horn antennas really took off.
Why?
Well, it was largely because of the development of radar technology.
Yeah?
Radar systems use rectangular waveguides for centimeter wave frequencies, and rectangular horn antennas were a natural fit for those waveguides.
So the horn shape was basically an extension of the waveguide.
Exactly like a controlled flaring out of the waveguide.
Okay, that makes sense. Now, I remember the thesis mentioned something about a trade-off with horn antennas.
Oh yeah, there's a really important trade-off between the size of the horn and the frequency it operates at.
Tell me more.
Basically, lower frequencies require larger horns.
So you can't have a tiny antenna working at a really low frequency.
Not really.
Hmm.
You need that physical size to effectively radiate those longer wavelengths.
Okay.
The thesis also mentions these things called ridges.
Ridges.
Yeah, ridges. They can be added to horn antennas to enhance their bandwidth.
So like a wider range of frequencies.
Exactly. It's similar to how ridges work in waveguides.
But they didn't use ridges in this particular research, right?
No, they specifically focused on enhancing the antenna without adding ridges.
At least initially.
Right. Initially, they were exploring other ways to improve performance.
Okay, so we've talked about the history a bit. Now, what about the different types of horn antennas?
Well, the thesis outlines 4 main types:
Okay, hit me with them.
pyramidal, E-plane sectoral, H-plane sectoral, and conical.
Conical uses a cone shape, I'm guessing?
It starts with a circular waveguide and flares out into a cone.
Okay, and pyramidal.
Pyramidal starts with a rectangular waveguide,
Uh-huh.
and it flares out on all 4 sides to form a pyramid with a rectangular opening.
Okay, and the sectoral ones.
They're only widened in one plane, either the E-plane or the H-plane.
What are those?
The E-plane is the plane that contains the electric field of the electromagnetic wave,
Okay,
and the H-plane contains the magnetic field.
got it.
So the sectoral horns, they're kind of like half pyramids.
So this thesis is all about the pyramidal horn.
Right, that's the star of the show.
Why that one?
Well, because it flares out in both the E and H planes,
Mm-hmm.
it generally has a larger aperture.
The opening,
Yeah, the opening, and that larger aperture allows for higher directivity,
which means
which means it can focus the radiated power into a narrower beam.
like a spotlight.
Exactly.
Right.
And higher directivity means higher gain in that direction.
So more power where you want it.
Precisely. And the thesis also mentions that pyramidal horns are usually used with rectangular waveguides,
Which transmit.
linearly polarized electromagnetic waves.
Okay, so the signal starts in the waveguide, and then the horn shapes and focuses it.
That's the basic idea. Let's talk a little bit more about these waveguides.
Okay, sure.
They're pretty fundamental in microwave communication.
Like how?
Well, they act like transmission lines, guiding the electromagnetic energy with minimal loss
Where does it guide it?
from a source to an antenna, or from an antenna to a receiver.
Okay.
And this is especially important at microwave frequencies,
Why?
because traditional transmission lines, like coaxial cables, become less efficient at those frequencies.
What happened?
You get things like skin effect and dielectric losses.
Skin effect is when the current only flows on the surface of the conductor.
Yeah, exactly. And that increases resistance, so you lose more power.
Not good.
No, not good. And waveguides help to avoid that.
I see.
Another important thing about waveguides is that they have a cutoff frequency, meaning they only work properly above a certain frequency.
So you need to choose the right waveguide for the frequency you're using.
Exactly. And they're usually made from highly conductive materials like aluminum, brass, or copper.
To minimize losses.
Right. And another interesting thing is that the internal dimensions of waveguides are often standardized.
By.
Organizations like the IE,
Why is that important?
it ensures compatibility between different systems.
So everything fits together.
Exactly.
So in this research, they used a specific waveguide.
Yeah, they used a WR62 waveguide for their Ku-band antenna.
And the dimension.
The thesis gives them as A equals 15.799 millimeters and B equals 7.899 millimeters.
Okay.
They also compare it to the WR137 waveguide, which was used in the base paper they were working with.
So different waveguides for different frequency bands.
Exactly. And the thesis actually has a table 1.1,
Okay.
that lists the specs for several different WR series waveguides, including WR90, WR137, WR42, and WR62.
What kind of specs?
Their operating frequency ranges and their internal dimensions.
So they picked the waveguide that's specifically designed for the Ku band.
Right, the one that's best suited for those frequencies.
Now, the thesis mentions that you can't just directly apply waveguide theory to horn antennas.
That's a really important point,
Why not?
because the horn shape introduces some complexity.
Like what?
Well, they talk about something called phase error. It happens because the distance from the center of the waveguide to the edges of the horn's opening isn't uniform.
So the signal travels different distances?
Exactly. And that means the electromagnetic wave arrives at different points across the opening with slightly different phases.
And that's bad.
Well, for optimal performance, you want the phase to be uniform across the opening.
So the horn shape kind of messes that up a bit.
It does, and that's why you need specific analysis techniques for horn antennas.
Okay, so it's more complicated than just a waveguide.
It is. And the thesis also mentions that pyramidal horns have a pretty good bandwidth, typically around 10.1, meaning the ratio of the highest frequency to the lowest frequency they can effectively handle.
Okay.
And sometimes they can even achieve 20.1.
So pretty versatile.
Yeah, they can cover a wide range of frequencies.
Okay, so we've covered the basics of horn antennas and waveguides. Now we need to get into the language of antennas.
Right. Chapter 2 of the thesis dives into all the key terminology.
Which is probably going to be pretty technical.
It is, but it's essential for understanding how we describe and measure antenna performance.
Okay, so let's start with radiation patterns.
All right. So imagine a 3D map that shows how much energy the antenna radiates in every direction.
Okay.
That's basically the radiation pattern.
So like a visual representation of the signal strength.
Exactly. And the thesis mentions elevation and azimuth patterns.
Right.
They're like slices through that 3D map, so you get a 2D view of the radiation.
Okay.
And a typical radiation pattern will have a main lobe,
Which is?
the direction where the antenna radiates the strongest signal.
Okay.
And then there are minor lobes in other directions. Side lobes and the back lobe, which is the radiation in the opposite direction of the main beam.
Got it.
They also talk about normalized patterns.
What are those?
It's a way of scaling the patterns relative to the peak value
Why?
to make it easier to compare different antenna designs.
Okay, so the main lobe is good. That's where you want the signal to go.
Right, and you want to minimize those minor lobes
Right.
because they represent energy that's not going where you want it to.
Wasted power.
Yeah, and they can even cause interference.
I see. What's next?
Beam width.
Okay.
That tells you how wide the main lobe is.
In degrees.
Yeah, in degrees, it's an angular measurement.
Okay.
The thesis focuses on two specific beam widths.
Hit me.
The half-power beam width, or HPBW,
Okay.
that's the angle between the 2 points where the power has dropped to half of its maximum value.
Or 3dBB down.
Right, and then there's the first null beam width, or FNBW.
What's that?
That's the angle between the first points where the radiation pattern goes to zero.
So HPDW gives you an idea of how focused the main beam is.
It's exactly. A narrower HPBW means a more directional antenna.
Okay.
Then there's radiation intensity,
Which is?
the power radiated per unit solid angle in a particular direction.
Okay.
And directivity builds on that.
How so?
Directivity tells you how well the antenna focuses its power in a specific direction compared to an isotropic antenna,
An isotropic antenna being?
one that radiates equally in all directions.
So it's like a theoretical benchmark.
Exactly. And then there's gain.
Right. Gain is similar to directivity.
Right.
But it takes into account the antenna's efficiency.
Any losses.
Exactly. Any power that's lost as heat within the antenna itself.
Okay.
And gain is usually expressed in decibels or dB.
And a higher gain is better. Right?
Yeah. A higher gain means the antenna is more effective at directing power.
Got it. Okay, what about polarization?
Polarization, that's all about the orientation of the electric field, of the electromagnetic wave.
As it travels through space.
Right. The thesis mentions linear polarization, which can be vertical, horizontal, or oblique.
And circular polarization.
Which is?
Either right-hand circular RHCP or
Okay.
left-hand circular LHCP.
Okay.
And then there's elliptical polarization, which is a combination of linear and circular.
Got it. So why is polarization important?
Because the transmitting and receiving antennas need to have matching polarization
Why?
for optimal signal transfer. If the
Oh.
polarizations are misaligned, you lose a lot of power.
Like trying to catch a baseball with a tennis racket.
Kind of like that, yeah.
What else?
Field regions.
Okay.
The space around an antenna is divided into 3 regions.
Based on.
The characteristics of the electromagnetic field.
Okay.
You have the reactive near field,
Uh-huh.
the Fresnel region, which is also considered near field,
Uh-huh.
and then the Fraunhofer region, which is more commonly known as the far field.
Okay.
And for most antenna analysis, we're usually interested in the far field
Why?
because that's where we look at things like radiation patterns and gain.
Okay.
The thesis mentions the far field condition, a distance of 2d squared over lambda, where d is the largest dimension of the antenna,
Okay.
and lambda is the wavelength.
So you need to be far enough away to get accurate measurements.
Exactly. And in the far field, the waves are basically planar waves.
Meaning?
They're like flat sheets propagating outwards.
Okay.
And finally, we have input impedance, the impedance that the antenna presents at its terminals.
Where it connects to the transmitter or receiver.
Right. It has 2 parts, a resistive component and a reactive component.
Okay.
The resistive part includes radiation resistance and loss resistance.
What are those?
Radiation resistance is related to the power the antenna radiates,
Uh-huh.
and loss resistance represents power lost as heat.
So you want low loss resistance.
Exactly.
Right.
And the thesis stresses that the input impedance should be close to 50 ohms
Why 50 ohms?
because a lot of circuits are designed to work with that impedance.
So it's like a standard.
Yeah, a mismatch can cause power to be reflected back.
Okay, so we've got a good grasp of the terminology now. Let's talk about the research itself.
All right, so Chapter 4 of the thesis outlines their objectives and methodology.
What were they trying to achieve?
Their main goal was to design and enhance a Ku-band pyramidal horn antenna,
Specifically for?
satellite beaconing.
And they were using HFSS for this.
Right, they wanted to leverage the power of that software.
Just to remind us, what is satellite beaconing again?
It's a continuous signal that a satellite transmits.
Okay.
so the ground stations can track its position.
So a good antenna is crucial for that.
Absolutely.
The thesis also mentions validating the approximation method.
Yeah, that was a key preliminary step.
What is that method exactly?
We'll get into that in a bit.
Meh.
But first, let's talk about the specific improvements they were hoping to see.
Okay, what were they shooting for?
Well, they wanted to achieve higher gain and directivity within the Ku band.
Which would make the antenna suitable for?
Satellite beaconing, and potentially even television broadcasting. They also wanted a narrower beam width
Why?
for more accuracy in signal transmission and reception.
Makes sense.
They also aimed for low power consumption, minimal signal loss, and a cost-effective design.
So they had a lot of goals.
They did,
Mm.
but they were all about making the antenna as efficient and effective as possible.
Okay, so how did they go about achieving all this?
Well, their approach was what they called exploratory research.
Meaning?
They started with a thorough review of existing literature.
So they did their homework.
They did, and then they used the approximation method to get an initial set of design parameters.
Okay, let's talk about that method now.
All right, so it's a mathematical technique that helps you solve the design equations for a pyramidal horn antenna.
Those equations must be pretty complex.
They are, and the method involves taking input parameters like the desired frequency, the waveguide dimensions, and the target gain, and then using an iterative process to find a solution.
Iterative meaning?
You start with an initial guess, and then you refine it over and over until you get a value that satisfies the main design equation.
Okay.
The thesis actually mentions an initial approximation formula,
Okay.
which gives you a starting value for a key variable they call x.
What is XE exactly?
It's kind of a tricky one. It doesn't directly correspond to a single physical part of the antenna.
Okay.
Think of it as a factor in their mathematical model.
That helps them determine.
The overall dimensions of the horn, like its length and the sizes of its opening.
I see.
So they use X to fine-tune the design, and the iterative process makes sure that the final dimensions will meet their performance goals.
So X is like a behind-the-scenes player.
Exactly. It's working in the background to make sure everything comes together.
And they use MATLAB for this iterative process, right?
Yeah, they weren't doing these calculations by hand.
That would be a nightmare.
It would. The thesis even includes a flowchart 4.2,
Which shows?
how their MATLAB algorithm works, how it takes the input parameters, checks if the current value of he is good enough, and then updates it until they find a solution.
Very clever.
It is. And then they moved on to the design and simulation in HFSS.
Tell me about that.
Well, they have another flowchart 4.3,
Okay.
that details their workflow in HFSS,
That's the first step.
defining the 3D geometry of the antenna,
Based on?
the dimensions they calculated using the approximation method.
Okay.
Then they assign materials like aluminum for the waveguide and the horn,
Uh-huh.
and they set up boundary conditions to define the simulation space.
Like the virtual environment.
Exactly. And then they excite the antenna.
Meaning?
They use a wave port to feed electromagnetic energy into it through the waveguide.
Okay.
And they define the frequency range, which is the Ku band.
Makes sense.
And they set up the simulation parameters.
Right.
Things like the meshing, which affects the accuracy of the results.
Yeah.
And finally, HFSS calculates all the results,
Which they can then.
visualized in all sorts of reports. Things like S parameters, VSWR radiation patterns, gain directivity, all the good stuff.
So HFSS is like a virtual antenna testing lab.
Yeah, exactly. They can build and test the antenna virtually
Tweaking parameters and seeing what happens.
without having to build physical prototypes.
That must save a ton of time and money.
Oh, absolutely.
So they started by replicating a design from a base paper, right?
Yeah. Chapter 5 talks about that.
Why did they do that?
It was basically a validation exercise
We make sure.
that their methods and their use of HFSS were reliable.
Makes sense.
They took a design from a 2015 paper they had published.
Also about horn antennas.
Yeah, but that one was for an X-band antenna.
So a different frequency range.
Right, but they used the same approximation method and the same design equation.
Okay.
The base paper used a WR137 waveguide and operated at 7 gigahertz with a target gain of 15 dBe.
Yeah.
And they got really close agreement between their new simulation results and the results reported in the base paper.
That's good, right?
It gave them confidence that their approach was solid before they moved on to designing the new Ku-band antenna.
Okay, so Chapter 6 is where they get into the nitty-gritty of designing the Ku-band antenna.
Exactly. They lay out all the design equations.
How many are there?
11 of them. Equations 6.1 through 6.11.
Wow.
And they, again, emphasize that iterative process in MATLAB to solve for
Okay.
And based on all that, they calculated the exact dimensions for their Q-band pyramidal horn antenna.
Using the WR62 waveguide.
Right.
And those dimensions are...
They're all listed in Table 6.1.
Give me some highlights.
Well, you have the internal dimensions of the waveguide itself, A and B,
Uh-huh.
then the aperture dimensions of the horn, A1 and B1,
Okay.
and then the slant heights of the pyramid, faces PE and PH,
Got it.
and the lengths of the horn in the E and H planes, LE and LH.
And they also specified a wall thickness.
Yeah, a 0.5 millimeters.
It's a lot of precise measurements went into this.
Absolutely. It's all about getting those dimensions just right.
And then they had to create the 3D model in HFSS.
Right? They described that process too.
How did they do it?
They started by creating the waveguide and the horn as separate 3D boxes.
Okay.
And then they used Boolean operations to create the hollow interiors.
What are Boolean operations?
They're like ways of combining or subtracting shapes.
Uh-huh.
So they subtracted shapes to make the waveguide and the horn hollow.
Okay.
And then they used another Boolean operation to join the two sections together.
So they basically built the antenna piece by piece in the software.
Exactly.
Okay, so now we get to the enhancement part.
Right. This is where they try to make the antenna even better.
What did they do?
They added a dielectric microwave cavity
Where?
behind the wave port,
Which is?
the point where the signal enters the antenna.
Okay.
And the material they used was Rogers RT-Duroid 60106010LM.
What's special about that material?
It has specific electromagnetic properties.
That helped to.
Absorb radiation.
Okay.
So the idea is that the cavity will absorb some of the radiation from the back and side lobes of the antenna.
Reducing interference.
It's exactly, making the main beam more focused.
I see.
And the cavity can also improve impedance matching.
How so?
It can help transfer power more efficiently from the source to the antenna.
Okay, so the cavity's like a little helper that cleans up the signal.
You could say that.
Okay, so Chapter 7 is where we see the results.
Right, the moment of truth.
Let's start with the basic antenna without the cavity.
Okay, so first we have the scattering parameter S11, or return loss. Figure 7.9 shows that the return loss was below -30 dB across the entire Q-band.
Which means
very little power is reflected back.
So a good impedance match.
Exactly.
What about VSWR?
Figure 7.Nella shows a VSWR of less than 1.4 across the Q-band.
Which is also good.
Yeah, a VSWR below 2 is generally considered acceptable, and below 1.4 is really good.
So the basic design was already well matched.
It was. Then we have the 3D power radiation pattern at figure 7.11.
Okay.
It shows a maximum radiated power of 41.1251 dB,
And the gain.
23.476 dB,
And directivity.
22.909 dB.
Which were close to their calculated values.
Right. Figures 7.0 and 7.13 show the 3D gain and directivity patterns, and figure 7.15 shows gain versus theta.
So the basic antenna had a pretty good gain and a focused beam.
It did.
What about the 2D radiation patterns?
Figures 7.16 and 7.17 show them at phi equals 90 degrees. They show that the maximum radiation is at theta equals 0 degrees,
Which is?
the direction of the main beam.
Okay.
Then you have the impedance plot in figure 7.18.
What does that tell us?
It shows how the antenna's impedance varies with frequency.
Okay.
And figure 7.15 shows wavelength versus frequency.
Anything interesting there?
Not particularly, it's just the expected inverse relationship.
Okay, so those plots give us a baseline understanding.
Right before we add the enhancement.
So let's talk about the enhanced antenna, now the one with the cavity.
All right, so across the board, the enhanced antenna showed improvements.
Starting with?
Return loss, figure 7.20, shows that the return loss dropped below -32 dB.
Even better.
Yeah, even less power reflected back.
Impressive. What about VSWR?
Also improved, figure 7.21 shows it staying below 1.35.
So the cavity really helped with impedance matching.
It did. Now for the radiated emission gain and directivity,
Okay.
figure 7.22 shows the 3D power pattern with a slightly higher maximum power, and the gain increased to 23.780 dB,
Nice.
and directivity to 23.185 dB.
That's a decent improvement.
It is, and figure 7.25 shows that the side lobes might be suppressed too.
Which is good.
Yeah, it means more power in the main beam.
Exactly. What about the 2D patterns and the impedance plot?
Figures 7.26 and 7.27 show the 2D patterns with a more focused main beam.
Okay.
And figure 7.28 shows the impedance plot for the enhanced antenna.
Anything noteworthy there?
It's just slightly different from the basic antenna, which makes sense because of the cavity.
Okay.
And the wavelength plot in figure 7.29 is basically unchanged.
So the cavity didn't affect that.
Right.
Okay, so the thesis wraps up with a performance evaluation.
Right.
And they refer to some figures that we don't have in front of us.
Figures 7.3 through 7.32.
But they basically say that the cavity led to noticeable improvements.
Exactly, especially in return loss and gain.
So their enhancement technique worked.
It did. They achieved their goal.
And they did it with a relatively simple modification.
Right, just adding that dielectric cavity.
Pretty clever.
It was, and it shows the power of simulation tools like HFSS.
So for you, our listener, the key takeaway here is that they successfully designed and enhanced a Q-band pyramidal horn antenna.
They used the approximation method and HFSS to create a solid design.
And then they boosted its performance with that dielectric cavity.
It's a great example of how to optimize antenna design.
It makes you wonder what other enhancements are possible.
Right. What other clever modifications could we explore?
Maybe for even more specialized applications.
Like advanced satellite communication or radio astronomy.
It's a fascinating challenge to balance complexity with performance.
Absolutely. There's always room for innovation in antenna design.
Well, thanks for joining us on this deep dive into Q-band pyramidal horn antennas.
It's been a pleasure exploring this research with you.
We'll catch you next time.
Until then, happy antennaing.